life's been on Earth for 3.8 billion years. And in that time, life has learned what works and what's appropriate here and what lasts here. And the idea is that perhaps we should be looking at these mentors, at these biological elders. They have figured out how to create a sustainable world. So rather than inventing it from scratch, why don't we take our cues from them? These are earth-savvy adaptations. They're the consummate life. These organisms are the consummate engineers. They're the consummate chemists and technologists. They've learned how to do it in context. So that's the core idea behind biomimicry, is that the best ideas might not be ours. They might already have been invented. Biomimicry is innovation inspired by nature. It's a new discipline in which the people that make our world, the chemists and architects and material scientists and product designers, they ask themselves, what in the natural world has already solved what it is I'm trying to solve? And then they try to emulate what they've learned. Our work as a species is to create designs and strategies that move us towards being better adapted to life on Earth over the long haul. And when you ask how to be better adapted to this planet, there are no better models than the species that have preceded us for billions of years. You know, there are 30 to 100 million species, maybe more. And in all that diversity, there is a hidden unity. There are a set of operating instructions, how to be an earthling. And they're life's principles like life runs on sunlight, except for a few organisms in sulfur vents at the bottom of the ocean. Life runs on current sunlight. We run on ancient photosynthesis, trapped in fossil fuels. Life does its chemistry in water as the universal solvent, and we tend to use very, very toxic solvents like sulfuric acid. Life depends on local expertise. Organisms have to understand their places. They have to know the limits and the opportunities of their places. And life banks on diversity and rewards cooperation. Life wastes nothing, upcycles everything, and most of all, does not foul its nest, does not foul its home. We're a very young species, and probably our best stance as a young species is to be apprentices to these masters. We need to replace our old industrial chemistry book with nature's recipe book. Our synthetic chemistry is completely different than nature's chemistry. We use every element in the periodic table, even the toxic ones. And then we use brute force reactions to get elements to bond or break apart. Life uses a small subset of the periodic table, the safe elements, and then very, very elegant recipes. Low temperature, low pressures, low toxicity. That's nature's chemistry. It's a very different paradigm. And we have to ask ourselves, not just how to replace individual molecules for different kinds of molecules, but rather whole families of reactions. It's a big job to do that, but it's an Apollo project worth pursuing. Organisms make materials in and near their own body. So they can't afford to heat things up to astronomical temperatures or to use toxins or high pressures. So for instance, a spider, it takes what comes into its web. A fly flies into its web, it takes that, it does chemistry in water at room temperature, at very low pressures, and it creates this amazing fiber that ounce for ounce is 5 times stronger than steel. And this is being looked at now by fiber manufacturers. Nature's also really good at making hard materials like ceramics. If you take the inside of an abalone shell, which is that iridescent mother of pearl, that material is twice as tough as our high-tech ceramics. And what those mother of pearl layers are composed of is just very simple materials in seawater. So what happens is the soft-bodied critter releases a protein into the seawater, creates a template, and on this template there's charged landing sites. And the calcium and the carbonate in the seawater is also charged, and it lands in particular sites, which directs the crystallization, automatic self-assembly crystallization of this incredible material. And actually it's a self-healing material. Beautiful architecture, incredibly benign manufacturing. And people are figuring out how to make ceramics without ever using a kiln. And this has been looked at for both reasons, for the blueprint and for the recipe of how you self-assemble out of seawater a hard material. The one thing that we have an awful lot of is carbon dioxide in the atmosphere. And we think of it as the poison of our era. Life sees carbon dioxide as a building block. Carbon dioxide is used by plants to make sugars and starches and cellulose. It's used by organisms in the sea to make their shells and to make coral reefs. And that chemistry, that CO2 to stuff chemistry, is now being mimicked. So Novomer is a company that takes carbon dioxide and turns it into biodegradable plastics. There's also a company called Newlight, and their product's called Air Carbon, and they're taking methane, which is an even worse greenhouse gas, and they're using that to create packaging. Dell is using all their packaging now made out of this air carbon, it's called. There are chairs made from it, the first carbon negative chairs in the world made of this kind of plastic that comes from CO2. The most used building material on the planet is concrete. The manufacture of concrete produces 5 to 8% of all CO2 emissions. But when you look at a coral reef, which is a concrete-like structure, you realize that CO2 is actually sequestered. So there's a company called Blue Planet that is now taking the recipe from the coral reef, and they're taking CO2 from flue stacks, and they're taking seawater, putting those together and precipitating out the raw materials for concrete. And in fact, they're now able to sequester a half a ton of CO2 for every ton of concrete. So if you can imagine someday us using carbon dioxide and sequestering it, long-term geological sequestration in the buildings that are all around us. That's what's exciting about biomimicry. You say to yourself, there's existence proof that there's another way to do this. In the arena of conserving energy, there's a software company called Regen, and they've studied how ants and bees communicate to one another in order to find food sources and to help streamline their foraging. And what they've done is they've applied these algorithms to sensors that they're able to put on appliances and drastically reduce peak demand by 25 to 30%, reducing energy bills by having these appliances communicate with one another and dial down the need for energy. At Caltech, students have come up with a new kind of wind farm that's based on how fish move in a school. So when fish are moving, they group together, and the ones in the front, with their sinuous movements, they kind of throw off vortices, these little spirals in the water. And then the ones behind them curve around those spirals, and actually they get flung upstream, saving a lot of energy. So what these students did was they said, why don't we take vertical axis wind turbines, and instead of spreading them out on the landscape, like you would with traditional wind turbines, why don't we pack them as closely as possible together? And they did this, and they found that when the first axes turned, they would create these spirals, and the ones behind them would start to turn even before the wind hit them. And they got 10 times more wind power out of a wind farm this way with a lot less land use. One of the things a thirsty planet will need is a way to find more fresh water. The Namibian beetle lives in the Namib Desert, drinks entirely from the fog that comes in a few times a week. It has these special structures on its wing scales that condense the water out of fog very, very efficiently, 10 times better than our fog-catching nets. This Namibian beetle effect has been mimicked by many companies trying to make new fog-catching nets for agriculture along fog coasts. There's also a small company that's called NBD Nano, and they're creating the fog-catching surface along the inside of a water bottle and creating a self-filling water bottle that will fill itself with the humidity in the air. Life is really good at filtering, especially to recover fresh water. If you think about a fish, every fish in the ocean is a desalination plant. It's living on fresh water in its cells, but it has to create that fresh water from salt water. So it's desalinating. So this idea of nature's membranes, we even have them in our bodies. We have them in our kidneys and in our red blood cells. And we have these little pores called aquaporins. And what they do is they actually, because of their shape and their charges, they are perfect for water molecules. Water molecules are attracted to the pores, to the channels, and then they move through them very, very easily, leaving everything else behind. And that's been mimicked in a membrane with a Danish company called Aquaporin. And they're doing desalination membranes that, instead of the energy-intensive reverse osmosis, which pushes water against a membrane, they're using the aquaporin membrane to pull water molecules through in something called forward osmosis, a fraction of the energy use and about 100 times more permeable than the normal membranes that we use in our big desalination plants. Agriculture is one of our biggest uses of water. And if we can find a way to grow plants with less water, that's going to go a long way for a thirsty planet. What scientists are doing is that they're looking at places where plants are growing in extreme conditions and asking, how are you doing that? A guy named Rusty Rodriguez went to the Yellowstone hot springs. And these hot pools have a grass growing around them called panic grass, which shouldn't technically be able to live in those conditions. But he dug down in the roots and he found that there was a fungal helper wrapped around the root that was allowing the plant to grow in these very hot conditions. And he was able to inoculate seeds with a fungus that enabled the plant to grow 5 times more rice with half the water use, which is really, really important if we're talking about a climate-changed world where drought is the new normal. What's really interesting is sometimes you are asking yourself how to replace a chemical. And when you look to the natural world, you realize there's a big paradigm shift because you don't even need the chemical. Life often uses shape instead of chemistry. So for instance, paints. These are chemical pigments. Often we use really toxic materials like chromium or cadmium in our paints. And the question is, can you create color without chemistry? Can you create it with structure? Turns out that some of the most brilliant organisms in the natural world create their color through playing with light, through structure. So these are the hummingbirds and and the morpho butterflies and the peacocks. A peacock's feather has no pigment in it except for brown. All of those colors that you see are created from very simple layers that are a certain distance apart, and when light comes through, it gets bent, it gets refracted, it gets amplified to create the color blue to your eye, or the color yellow, or the color gold. All without chemistry. It's just structure. And structural color is 4 times brighter than pigmented color, never fades. Imagine if we were able to create products where the last few dip coatings of the surface of the product, say a car, would be transparent layers that played with light in such a way to create a color. No painting, no repainting. It's built right into the structure of the product. Another kind of chemistry that we're always looking for alternatives to is a better soap, a better way of cleaning without phosphates and other things in our wastewater. And life also has to stay clean. Imagine a leaf has to stay clean in order to photosynthesize. So scientists a couple of decades ago put a lotus leaf, put that under a microscope, and found that the way it stays clean is not a chemical solution, it's actually a structural solution. It has tiny bumps, they're a certain distance apart, and they're waxy, and rainwater balls up on this surface. And dirt particles don't really adhere, they kind of teeter on the mountaintops. And the ball of rain, when the leaf tilts, picks up those dirt particles as it rolls off, pearls it away. And it's become known as the lotus effect. So now there's all kinds of products. There's fabrics with the lotus effect. Big Sky Technologies does that, and Scholler, and there's roofing tiles, Earless roofing tiles. There's a paint from a company called Stowe called Lotusin. And when it dries, it has that bumpy structure so that dirt really can't adhere, and rainwater cleans the building instead of sandblasting or applying chemicals and soap. So it's a whole new way of cleaning. It's another one of those paradigm flips that you often see in the natural world when you look to nature for solutions. The big problem of superbugs in hospitals and the fact that we use so many antibiotics in order to battle bacteria. So for instance, there's a company called Sharklet. They said, how does nature manage bacteria? They found this very interesting shark, the Galapagos shark, which is a basking shark, that has no bacteria on its surface. Even though it doesn't move very much, it has no bacteria on its surface. How is that possible? Well, the shape of its skin turns out to be something that bacteria do not like to land on or to form their films on. So by mimicking that shape, Sharklet Technologies has created thin films that you can put on doorknobs and hospital bed railings, and all kinds of surfaces. And what the shape does is it actually repels the bacteria. It's a shield against bacterial infection, but it's not done with chemistry. It's done with structure. You know, the answers we seek, the secrets to a sustainable world, are literally all around us. And if we choose to truly mimic life's genius, the future I see would be beauty and abundance, and certainly fewer regrets. You know, in the natural world, the definition of success is the continuity of life. You keep yourself alive and you keep your offspring alive. That's success. But it's not the offspring in this generation. Success is keeping your offspring alive 10,000 generations and more. And that presents a conundrum because you're not going to be there to take care of your offspring 10,000 generations from now. So what organisms have learned to do is to take care of the place that's going to take care of their offspring. Life has learned to create conditions conducive to life. And that's really the magic heart of it. Life creates conditions conducive to life. And that's also the design brief for us right now. We have to learn how to do that. And luckily, we're surrounded by the answers and, millions of species willing to gift us with their best ideas.